Bismillahirrahmanirrahim. Beta, today we are going to discuss the second last point today, that is equilibrium. Equilibrium we have done in O level. There are two conditions for equilibrium. An object is said to be in equilibrium if condition number one, if the resultant force acting on it is zero, means the balanced forces are acting. And when the forces are resultant force is zero, if there are two forces, the two forces are equal to each other, right? Force towards right is equal to force towards left. Force upward force is equal to downward force. If there are more than two forces and we arrange them according to head to tail rule, they will end where they started. They will end where they started. We have already discussed, don't you think so? In
Yes, sir. In
Newton's
vectors.
first law, arrange the forces F1 where F1 ends, the F2 starts, the F3 ends where the first force starts. Then the resultant force is said to be zero, right? So these are resultant forces, balance forces, and this is the first condition of equilibrium. The second condition is sum of clockwise movements acting on the object should be equal to sum of anti-clockwise movements. It means, in other words, the net moment or net torque is zero. And what is that? It is sum of clockwise movements because turning can be either clockwise or anti-clockwise. Sum of clockwise movement is equal to sum of anti-clockwise movement. Now, you have to consider these 2 points. We will discuss. Sometimes the resultant force is zero, but the clockwise movement is not equal to anti-clockwise. If one condition is fulfilled, like resultant force is zero, then we call it a linear equilibrium. But that is not complete equilibrium. Let me tell you. Sometime we will see this example. The clockwise movement is equal to anti-clockwise movement, but resultant force is not zero. Then we saw it is in rotational equilibrium. It is not complete equilibrium. So for complete equilibrium, both conditions should be fulfilled. What is that? Resultant force should be zero as well as the clockwise movement should be equal to anti-clockwise movement. Clear? Now we are going to discuss some example of this. The clockwise movement and done in the O level. Hassan, you will remember. Consider this is a fire brigade, fire extinguisher uh, truck. I have made a simple diagram. Sorry for that. And this is a ladder on which a fireman is there with a pipe. And the weight of the fireman is 840 Newton. Hassan, if you remember, the same reading we have done and same reading has come in the past paper. This is a paper question in O level actually. So
Yes, sir.
the weight of the fireman extinguisher is 840 Newton. Can you tell me which type of movement this creating if the pivot of the ladder is there? Is it clockwise or anti-clockwise?
Clockwise.
Very well answered. It's producing clockwise movement, right, Sarosh? So to have it balanced, we need an anti-clockwise movement. So where the anti-clockwise movement is coming from, you see the fireman is having a hose or pipe which is throwing the water at very strong force speed towards the right. Like when somebody shoots a gun, he feels a recoil backside, backwards. So same is going to happen here. when the fire extinguisher sprinkles the water forward, it feels a backward force on the fireman that will create an anti-clockwise movement, right? And actually, this force, recoil force, the F, with which I have marked as green, this is the force we wish to find, right? And here, the one of the force is 840 Newton, other we have to find. And we know these distances 16, 12, and 20. So we have to find the force F. Will you help me? How would you find that force? G. So our
Sir, do
basic
we need the
formula,
angle for that?
no, not here. It's all level question, so no angles involved. Maybe in the next question, yes, definitely angles are involved there. So what is our basic formula? The clockwise movement is equal to anti-clockwise movement. Now let me tell you, these are not the standard abbreviation. I'm just writing for my convenience. So here the clockwise is 840 and the anti-clockwise force is F, which we have to find. And moment we need actually. The moment is force multiplied by perpendicular distance of each object. Can you help me? Which distance will you multiply with 840? Surosh, Hassan. Out of these
20?
three distances, 20, 16, and 12.
20.
No. Hassan, you're wrong. Surosh is correct. It is 16. We need the perpendicular distance. The direction of force is this, and only this distance, 16, is making 90 degree with this direction, right? So we
Yes,
multiply
sir.
each force with a distance which is perpendicular to the direction of force. It is 16. Now we have to find F, and F will be multiplied by which distance? Can you help me?
12.
12, very right. It makes 90 degree with this. Actually, the direction of force is going there, and we have to take distance from the pivot, which is making 90 degree. And as this distance, it is making a rectangular, will be equal to this one. So 12 is the distance. The opposite sides are equal in a rectangle. If you see, there is a rectangle being made, right? And opposite distance. Mr. Rosh and Hassan, can I remove this?
Yes, sir.
Okay. Part. This is again a good question. We are going to do that. Consider there is a rod, right? And that rod is pivoted here with a screw, so the rod can rotate. And when you will leave it, where will which is connected to this point of the wall and to the right end of the rod, and is stretching. The force applied by the rod or wire or a thread or a string is called tension. Stretching force. That is 15 Newton acting at 20 degrees with the rod. The length of the rod is L. What will be the weight of the rod? I'm waiting for you to answer. What will be the weight of the rod?
If the rod is in equilibrium, means that the force acting
Yes,
upwards
it
will
is
be
in
equal to it.
equilibrium.
So the force upwards will be 50 sine 20, and that will be equal to weight.
Very right. Beta, we are not giving, we are only giving the force upwards. So we will multiply F weight from the center will be half the length, right? So weight will be multiplied by L over 2. And as the force 50 Newton is making angle 20°, so that will be whenever we are having a force making some angle, the formula is F into R into sine of theta. So we will multiply F is 50, R is the length, this whole length, because here the distance is this much, and sine 20°. Oh, can you hear me now?
Yes, sir.
Hassan and Soch, can you hear me? Okay, beta, will you be able to understand this question?
Yes, sir.
Yes.
I'm going to repeat. If the weight is not weight, we have to find the weight acts at the point which is at the center of the rod. So its distance from the pivot will be half the length. And for other, the formula which is force making some angle formula is FR sine theta. Here R will be this distance from the pivot. That will be the whole length and sine of 20°. Now L will be cancelled with the L and W we can find. Clear? Can I
Yes,
remove
sir.
it now? Hassan, will you be able to understand?
Yes, sir.
Hassan and Srosh, can I remove it, beta?
Yes,
Yes.
sir.
Hassan and Srosh, can you hear me clear? Can I remove
Yes,
it?
sir.
Yes, you can remove it.
Okay. Okay, beta ji. Now, the next last question, and that is giving you example of a couple as well. Beta, sometime now we have a machine which is made up of multiple parts, and the some parts they are uh, connected to one part connected to other using the shaft or gears, and the situation is like that you rotate one part in some direction, but the other part connected to that will be rotating as well, but it would be in opposite direction or in different direction. Like the steering in the car, the steering rotates in front of you parallel, but the wheels are rotating of the car, they rotate in different direction. Do you see? They are related, connected with each other, but their rotations are different. So the situation is like here we are having a handle, shaft you can say, that is connected to a wheel, and you are rotating that shaft in anti-clockwise direction, means you are applying an inward force here and outward force towards yourself on this end, and two equal and opposite force make a couple, and the distance from end to the center is 30 centimeter for this shaft, and there is a wheel which is lifting a weight of 90 newton and its radius is 10 centimeter. Now the both the moments are in equilibrium, the whole scenario system is in equilibrium, so we have to find the value of this force, right? And keep this in mind, this makes a couple. So what is our basic formula? Clockwise moment is equal to the anti-clockwise movement. Here, this one is creating an clockwise movement, and its force is 90 Newton, and distance from the pivot will be 10 centimeters. Let me tell you, you don't need to convert centimeter into meter, because if we are using a formula where we have same quantities on both sides, like we are having movement here clockwise and movement here as well, but that is anti-clockwise, but both are movements. So in that situation now we do not need to use the standard unit, we just need to keep the units same. So we can use the units in centimeters. So this 90 will be multiplied by 10 centimeter, and force. This is here. In couple, we do not take distance from the pivot. Actually, we take the distance between the forces. If this to this side is 30, the distance between the forces will be double of that. That will be 60. The rest you can solve. So the only point here which we need to, whenever we are having a couple, we take the distance between the forces, and that will be 60 here. Do you understand this? Dear Hassan and Suroj, will you be able to understand?
Yes.
Ji beta, will you be able to understand? Should we continue? May I go?
Yes, sir. Yes, sir.
Okay, okay, beta ji. Now, there are three examples. Let me see you. We have done this in O level as well. Here we are having two forces. So, can you, beta, please tell me, is this system in equilibrium? Yes or no?
No.
Is this system in equilibrium? No. Very well asked. Why it is not in equilibrium?
It has no clockwise force, only anti-clockwise force.
Very well. So, resultant force is zero, right? But the anti-clockwise moment is not equal to clockwise, because they both are anti-clockwise. There is no clockwise. Very well answered. What about the second one? Is this in equilibrium? Yes or no? Ji beta. What about this one?
Yes, sir, it is.
Is this in equilibrium?
Yes, sir.
No, it is not in equilibrium. Why? No, it is not. Because this one is clockwise and anti-clockwise are equal to each other. But both the forces are in the same direction. They forces in the same direction, they add into each other. The resultant force is not equal to zero.
Motion. So
Yeah,
linear force is there.
clockwise movement is equal to anti-clockwise. So it is not in equilibrium. It is in rotational equilibrium. And it was in linear equilibrium. Clockwise movement is not equal to. So this was in linear equilibrium, and this one is in rotational equilibrium. What about this one? Third one.
Third one is in equilibrium.
Very right. Why? Because the resultant force is zero and one is anti-clockwise, the other is clockwise. So anti-clockwise movement is equal to clockwise movement. So very well answered. Now, Let's see. Do you think this is in equilibrium? This object, this scenario? What do you think? Clockwise movement is equal to anti-clockwise movement. Yes. But here, two downward forces will add up, make a larger downward force, and upward force will cancel only one of those. The total upward force is not equal to total downward force. This is not in equilibrium. But if we increase the upward force to like that, then it can be in equilibrium, right? Clear?
Yes.
Yes, sir.
Now we are going to discuss the last point, resistive forces. So resistive forces now, which are opposite to motion, which oppose the motion of an object. So when the any object is moving, a solid object, and that is contact with a solid surface, then that opposing force, which the force which opposes the motion of two solid surface in contact, that is friction, right? Friction is between the solid surface. But if an object is moving in air or in water, then water and or air will apply an opposing force on it. So the opposing force applied by any fluid on an object which is moving inside the fluid, that is not friction. That is viscous drag, or you can simply say them as drag, right? So beta, we usually used to think friction and drag forces, air resistance, they are similar. No, they are different. The friction is between the solids, and friction depends upon the roughness of the solid surfaces or area in contact. Like for a normal tire, the area contact is this much, but when it is punctured, you see the area in contact is now larger than as compared to its normal situation. So there is more friction. And the friction also depends upon the weight of the object. But the drag forces, which are applied by fluid means both liquid and gases, depends upon the speed. It depends upon the speed. The faster the object, the larger air resistance it feels. Or the surface area, the front area. You know that why the aeroplane bullets, missiles are made narrow in the front. It is caused to reduce the effect of drag, and it also depends upon the density of the fluid. Like the water is more denser than air, so water friction is more stronger than air resistance because it is more denser. Like you throw anything in the air, a stone, it will go some distance, depends upon how much force you have applied. But with the same force, you throw a stone inside the water, it will come suddenly. Within a moment, it will come to a very slow speed. That water makes the particle object slow very fast as compared to air because it applies larger drag force. Now, friction can be very useful for us. Friction is used to start a motion or stop a motion. We cannot start a motion on a solid surface or stop a motion if we do not have any friction. Friction is used to give the grip uh, for motion of an object, to grip the objects when we have to lift a weight. The weightlifters, they dry their hands by using the powder. That is not for any cosmetic reason. That is to make dry up the hands. And the screws, they have lining threading on them. That is to produce friction. Friction gives us the fire. Whenever we have to make a fire, we rub the matchstick or a stone against another stone. So the friction gives us heat and fire. Now, the main point over today's concern, the friction can be in forward direction as well. Can you give me example in which situations the friction will be forward? So there can be a thousands or millions of examples. We cannot discuss or mention all here, but let us see. The friction can be in forward direction. The example is on the wheels. Like a car is moving in this direction. So this is the direction of motion of the car towards the right. And the wheels, if you consider now, will be turning like that. So when the wheels are in contact with the ground, the wheel is moving the turning towards clockwise backward. So we are considering only this part. When the wheel is turning like that here, the wheel is going towards the left, and the friction is always against the movement against the movement. So friction here on the wheel will be in this direction. So beta, the friction on the wheel is in this direction, in the forward direction, right? But let me tell you, we are calling it is the friction on the wheel. But as all four wheels experience the friction and overall friction opposes the motion, so the overall friction on the car is towards the up, against the movement. But the friction on the wheel is not against the movement. Actually, it is in the same direction as its movement, right? Similarly, the friction on the foot, not friction on the person. Let's a person is walking, and when he is walking, he pushes the ground backward with his foot, right? And when the foot is pushing backward, means the foot is applying the force in this direction, trying to move the earth in this direction. The movement of foot at that position when pushing the earth backward is in this direction towards left, and the friction is against the movement that will be forward. So on the foot, the friction is in the same direction where the walker or the person is moving to, but overall friction is opposing. When we say the friction on the person, that will be against opposing the movement towards the left as the person is moving towards right. But friction on the foot is in forward direction. Similarly, on an object inside an accelerating vehicle. Let's say when an object accelerates suddenly, picks up the speed. So which direction if you are sitting in the car and the car picks up the speed very fast? Which direction do you feel the jerk? You feel the jerk backward now,
Backward.
and it means if you are moving to backward, the friction is against your movement. The friction will be in forward direction, right? Clear? Now the last three examples left. We are considering forces on the wheels. Now consider, make one thing clear. We are doing past papers question. If we are considering the forces on the wheel of a moving car, so let's consider one wheel. This is a car, and the car is moving towards right. We just discussed the friction on the wheel. We are not considering the forces applied by the car on the road. We are looking at the forces which are acting on the wheel, right? The friction on the wheel is in forward direction. As the car pushes the ground downward due to its weight, then the road will apply an upward force on the wheel. We are looking the forces on the wheel. So the downward force is on the ground, let me tell you. And on the wheel, the ground will apply the force on the wheel that will be upward. That is called as normal reaction. Contact force. That is always normal means perpendicular to the up. surface in contact. Normal means perpendicular. So here the normal force will be upward and friction is in this direction. So these two forces are acting, and where the resultant force will be, the resultant force is somewhere in the middle of two forces in this direction. So beta, the resultant force acting on the wheel will be in this direction. Please draw it. Done. Should we move on? Should we move on? Sarosh and Hassan,
Yes, sir.
can you hear me?
Done.
Sure.
Okay. Okay. Beta, consider this is a rod. Now we are considering the forces, resultant force on the rod. My rod is in contact with the two surfaces here and here. So at both these 2 points, we are going to consider the resultant force, right? So consider this is a rod. So if any way the rod is going to slip, so how would it move? This end will move to this side and this top will move towards down naturally. Is there any other possibility? So naturally, it goes like that. So this end will move towards slip like in this direction, and when it will move towards the right, the friction will act towards in opposite direction to the left, right? And the force applied by the surface on this will be normal reaction is always perpendicular to the surface. It will be upward. So at this end, we are having two forces, one and two. And resultant force is usually somewhere between these two forces. So let's say it is in this direction. So resultant force on the lower end will be this. Similarly, if the rod slips, this lower end will go towards the bottom, this end, and friction will be in opposite direction. That will be opposite. And the force applied by the wall on the road will be perpendicular to that. That will be in this direction. And resultant of these two forces will be somewhere in between the forces that is shown by this orange direction. So resultant force on the lower end is in this direction and the upper end of the road is in this direction. Right? Now the last point we are going to discuss, we are having three frames which are supported by two strings each. Here the forces are both strings are like that. Here one string is angled like that and one string is angled like that in third like that. So in each case, in these three diagrams, there are two of them are in equilibrium. One, this one and this one. This one is not in equilibrium. Why? That is going to be a very important point. Like these two forces which are in the same direction, they will have a resultant in the same direction in the middle of the forces. And the weight of the frame or the picture, it is a picture or frame, will be exactly opposite to the resultant tension. T tension, a force applied by the string is tension, will be exactly in same line with that. So resultant force of the tension and the weight, they both join at a point and they cancel out each other. So the object is in equilibrium. But here, if you see, we are having two angled tension forces. Strings are tension are angled, so are their tensions at angles. But this is not in equilibrium. Why? And the reason is, if you increase both the tension backward, they join at this point, and the weight is acting at the middle. They both are not acting at the same point. If you consider, beta, the center of gravity is here, and the forces join here. So where the forces join, their tension will be somewhere here in the middle of both the tension. But both the resultant tension and weight are not acting on the same point. So when two opposite forces, equal and opposite forces, act at two different points, they form a couple, and which makes object rotate. So that is not in equilibrium. But here, when you increase all the tension, both they join they join at the same point where the weight was acting. All the three forces are joining at one point, and the resultant of this point will be again acting on the same point, exactly cancelling the weight. So that is in equilibrium. But the important point, when three forces, they are increased behind, and they all join at one point. Such forces which meet at one point are said to be concurrent forces. And in that situation, all the forces acting at one point will cancel out each other. They will not form a couple, and the object will be in equilibrium. Right? But if the forces, all three forces are not joining at one point, their point of action is not same. They are acting two different points. When joined behind, they form a couple. They are not concurrent forces. And the couple, forming of couple, makes the object rotate like in this direction, and the object is not in equilibrium in this position. So this is not in equilibrium. So what is the basic point? If you increase all the forces behind their point of actions, and if all the forces join at one point, concurrent forces that make an object in equilibrium. If all the forces are not joining, meeting at one single point, they are not concurrent forces, they are not in equilibrium. Clear? Right?
Yes, sir.
Any question, beta?
No.